What's up, video watchers? Alan here for linear approximations and differentials. These things are intricate parts of the derivative if we were to break it down and take a look at it a little bit closer viewpoint. If you couldn't tell what we're going to be going over, it is these two things. And we're going to go ahead and start with this new concept called a differential, and also how to take and utilize the fact that we know what the derivative finds for us is the slope of a tangent, and therefore we have a tangent line. We can use this thing to approximate with a line, therefore called a linear approximation, for functions that are much more complex or difficult to work with. So what I'm going to start you off with is something that we should already know, something that we've done quite frequently, but just try to introduce some new terminology and viewpoints. So if we were to be asked to find the equation of a tangent line to some, hopefully it's differentiable function, f of x at some point we're going to call a. And we know we can use the point slope formula in order to come up with the equation of a tangent line. That means we would take the slope and replace it with the derivative. And if we were to use the 1 point, well, they gave us the x value and they told us how to find the y value. Then we would replace those things with to get a new-ish formula where our x1, y1 are our x and y values, and our slope is the slope of a tangent. That then is what we will use for any tangent line equation. So that will piggyback into what we're going to be talking about today in using lines to approximate, like we said, a function that may be initially given that's much more difficult to work with. So what do we mean by that? Well, if you take a look at a not too bad, but a challenging function we call a rational function, a ratio, a fraction, it's not the easiest to work with or do things to, like find the derivative. We got to take and rewrite it as x to the -1 and then do the power rule and then change it back. So if we were to say at our point of 2, we could just use what we just used up there, the a, plug that in, and we would get 1/2. And then taking the derivative and doing all of the things, we would get that 1/4 negative. So this would be the equation to that line without being simplified. We call the tangent line at that point, aka the derivative. Well, if you zoomed in right around that value of 2, you'll notice that when we do that, if you look a little bit to the right or to the left or locally, we talked about that before, around it, you'll notice that the blue and the orange don't seem to be much different. And again, notice how much we've zoomed in. Look at our y values now. Look at our x values now. So we're zoomed in quite a bit. And so if we wanted, we could actually use the equation of a line to find y values for certain x's, opposed to having to use this. And again, it's not that bad, just using a simple example at the beginning here. But that nasty function that is 1 over x. As we progress through this, we will be talking about a little thing called the linear approximation, or combining those two words, we would get a thing called the linearization. Okay, that is just an easier way, so to speak, of saying a linear approximation. We will therefore smash those words together and call it a linearization. And what we will be doing to that normal y minus y1 equals m times x minus x1 point slope form is we will be isolating our y by just adding over the y1. Now remember, the x1, y1, and m are changing in calculus. They will be that new format that I showed you at the beginning. And so it will now look like this, where we have our y value, or f of x. When we added this over, it was now equal to our y1. So at that 1 value, we're calling a, plus our slope, which is going to be of a tangent line, and then our a value as well. Now, of course, to make sure that you know that it is a linear approximation, we're going to put the little squiggly equal sign. Now, don't forget, we also said that we can just combine linear approximation into one word and call it a linearization. So to let you know that that is what we have done, we're going to rewrite it as L of x. We're not even going to put the squiggly equals approximate because we are telling you by writing L of x that it is the linear approximation and list it as that thing called a linearization. Oftentimes, this is actually what our calculators are doing to approximate things, but they can do it very quickly. We are going to at least see how it's all done and then lean on our calculators whenever we have to do things like this in the future. But before we do, we're also going to talk about one more application, manipulation of our derivative, and they are called differentials. And as you can see there, you can probably guess why they're called differentials, because we will be doing differentiation in order to take the derivative, and we will then look at these intricate parts named aptly differentials. So you know what differentials are because you know how to differentiate. That's our dy over dx, the change in our y's over the change in the x's. And remember, we use the lowercase d's to represent the derivative. Where originally, when we talked about slope, not of a tangent, but just slope of any 2 points, we called a secant, it was the change in our y's over the change in our x's that way, where we used a lowercase d in the Greek alphabet called delta to represent the difference. So let me try to explain this to you via a graph, a visual, if you will. If I told you my original function here is that y equals f of x blue line curve, well then if I picked some point, call it P, and I chose another one, let's call it Q, then you know the graph of that, I can find the slope of that secant line, and it would just be the change in my y over the change in my x. But if we took the derivative of this thing, then we wouldn't have another point on that curve. We would have just one and only one point because it's called a tangent for a reason. By definition, it would only hit once at point P. But in order to find the slope, whether it's of a tangent or a secant, we need 2 points. So look at this other one called R, which is on my tangent line. Well, then if I found the change in my y over the change in my x's, we're going to use dy and dx to represent those, because what did they come from? That was the tangent line, which is my derivative. And that's the gist of it. That is what we call differentials. It's going to change here and here, but notice it did not change there to there. Those values or differences will be the same, but the change in our y's will be different, and almost always you should have this one being the larger value. So the differences or increments between our 2 points P and Q, which remember was right here, are going to be obviously to the original function. And therefore, because it's the original, it's the old one, we're going to use those old Greek letters, delta y and delta x, the change in our y's over the change in our x's. But if we were to go from P and R, those are along my tangent line. And therefore, we will use the tangent function, we're calling it, or derivative, which would mean we will use our new letters, dy and dx. So if you notice, these differentials, we're calling them, are just the x and y distances between the 2 points on our tangent line equation. So just to reiterate, here's how I remember the 2 variations of the delta y and the delta x versus the dy and dx. The old or original function uses those old or original letters. Our new derivative function that we just learned a few weeks ago, we are going to use our new derivative letters, dy and dx. So to help you guys understand this a bit more, hopefully you're grasping it a little bit already, take a look at this. If we were to rewrite that slope of PR, which if you remember, PR was that new slope for our tangent or our tangent line. Then how would you write the slope? It would simply be the change in our y's over the change in the x's, but remember we're using the d's because it was from the tangent, which we know to mean f prime of x. It's the definition of the derivative there. And since those are equivalent, then what could we do to just solve for dy? We could simply just multiply both sides by dx to get rid of that difference in the x value distance and only be left with dy. It would be equivalent to the derivative of our original function times dx. And how could we write the delta y in terms of x? It would simply just be the difference in the two y values, which this is one, and then this would be the other, whatever this one is, plus the difference in our x values to find those two y values. Almost done here. Because we know that delta x and dx are the same and really small, then we know that delta y is simply just really close to dy. Again, let me show you the graph of this up above. Take a look at the very subtle difference between these dy and delta y. It's just that tiny little gap. So we are going to say that they are approximately the same. And therefore, we know that dy is approximately this then. And when we have our x equaling an a, that would mean we can replace all the x's with a's and get f of a plus our dy. So to recap everything that we've been talking about, we have the linearization, which again is just our function approximation with our line of a tangent, written in a little bit different form than our point slope form. As far as differentials go, remember those were a little bit different, no pun intended. That was when the dx and delta x are the exact same distance apart for both points on our curve and the tangent, but the dy was equivalent to f prime of x dx. Some of the other forms that we used, remember, was that as well. And to summarize everything, why are we even talking about all these? Well, remember, linear approximations are used throughout in order to deal with very difficult or challenging complex equations. To approximate it, to get it pretty close, but not exactly, we can use a much simpler function, like our line, using that technique we call linearization, rather than our original function. As for the differentials, those are the things that we will be talking about, discussing, and utilizing more in the future. So not so much now, but this, hopefully you recognize, is nothing new. It's just what we will be applying or using this for, will be. That's all I got for you in this one. Good luck, work hard, and continue to push forward. Until the next time, Coach Allen, signing off.